This is the introduction video to the integration method that we call integration by partial fractions. This method would be applied to three integrals that we have written here. What do they all have in common? Well, as we can see, within each integral we have rational functions. We're going to review rational functions down below in a few minutes. But let's start by refreshing the idea of partial fractions. So for that, I'm going to do the following example. Here it says add expressions, right? I have two rational expressions in fact. I need to add them. To add rational expressions, we use the same approach when we have to add two numerical fractions. So we know that to add any two fractions, they have to have same denominator. So when I look at those two expressions, I can see that their denominators are not the same. So first I need to think about the least common denominator. And in this case, since expressions are unique and they're not repeating, the LCD will be just the combination or the product of the two original denominators. So that's going to be the LCD. And that means that next I need to adjust each expression, each fraction, so that it has that denominator, right? I'm going to rewrite my original expressions. X plus 1 plus 3 over x minus 5. And here I'm going to show how I'm adjusting each so that it has that denominator. Okay, so my original denominator here is x plus 1. I want that, so it means that I need to multiply by the missing factor, which is x minus 5. And I have to multiply in the denominator and the numerator, right? Both. Same way we do it for numerical fractions. Now for the second expression, I have to multiply the denominator by x plus 1. That is the missing factor. And of course, I have to do that same thing in the numerator, right? Then now they have same denominators. It means that I'm ready to combine them, which is just writing them together in one fraction. So denominator is x plus 1 times x minus 5. I can choose any order I want, but they are essentially the same, right? And the numerator is 2 times x minus 5 plus 3 times x plus 1. Now the next step is to simplify the numerator, so I'll need to distribute 2. I'll get 2x minus 10, and then I will distribute positive 3, so that's plus 3x plus 3. Denominator is x plus 1 times x minus 5. And then finally, I get the numerator is 2x plus 3x, 5x. And then negative 10 plus 3, that's negative 7. 5x minus 7 over x plus 1 times x minus 5. Okay, so I just added two rational expressions. I'm going to rewrite my result this way. I'm going to write down what I started with. So I started with this 2 over x plus 1 plus 3 over x minus 5, right? And the result we obtained is 5x minus 7 over x plus 1 times x minus 5. So what we just did, we went this way, right? So we started on the left, we obtained result on the right, and that was addition operation. Now, if it was subtraction, if I had minus sign here, it would be the same process, right? So it means that I can say addition or subtraction. That's the way to go. But to obtain partial fractions, we have to go in the reverse direction. So going backwards, meaning starting with expression like that, starting with a rational expression like that, and rewriting it as the sum or difference of two or more fractions or simpler rational expressions. It's called partial fraction decomposition. Fraction decomposition. And that's the process that will help us to integrate the above functions. So that's how we can evaluate those fractions. They don't look too good right now, right? They look too complicated, but that's okay, because what we can do, and we're gonna learn this process a little bit more, we're going to decompose all those rational expressions into a sum or difference of simpler expressions that we would be able to integrate much easier. So for all those, we can, apply that process. Now, those examples, those integrals, we're not going to evaluate in this video. We're going to have separate videos for those. So this is just introduction. We're just learning about partial fractions. That's all we're doing here. Now, let's talk about, as I promised, let's talk about rational expression itself. So before you begin the process of partial fraction decomposition, there's like a checklist that you want to go over before you start. So first, and here's the general, the structure of the rational expression, right? Numerator, some kind of numerator, some kind of denominator. Well, in the numerator and denominator, we have to have polynomials. So P and Q should be polynomials. Let me remind you that polynomials are expressions that consist of terms where variables are raised to the whole powers. So I can't have, let me go back to more interesting examples. So expression that consists of terms where variables are raised to the whole powers only. So I can't have power 1/2, like let's say square root, or I can't have cube root in the polynomial, so only whole powers. So they're all polynomials. Some of them written in factored form, some of them are written in expanded form, right? So make sure that P and Q are both polynomials, and of course denominator cannot be 0. That's obvious, right? Okay, the next item on the checklist. P and Q have no common factors, meaning that if you factor each polynomial, you shouldn't see any common factors. And if you find common factors, it's like if I have x plus 1 on the top, and when I factor the numerator, if I can, I also have x plus 1 factor in the numerator. Well, if that happens, then we need to cancel them. We need to divide them out so that the final result has no common factors, and that's only when we start the process of partial fraction decomposition. Okay, so make sure you check that. Now, degree of the numerator is less than degree of the denominator, and that's when we say that rational expression is proper. Now, what is the degree? Remember, degree is the highest power of the polynomial expression. So if I look at the numerator here, its degree is 2, since 2 is the highest power. And if I look at the denominator, the degree of that polynomial is 3, because 3 is the highest power. So before we start partial fraction decomposition, we want to make sure that degree of the numerator is less than the degree of the denominator. That's what we call proper rational expression. What if it's not? What if the numerator has degree 4 and the denominator has degree 3? Well, then we have to perform long division. So we have to simplify our rational expression. And you can find more information. You can refresh long division of polynomials in any algebra or college algebra textbook. So that's another thing to check before you start. And now the last item is to look at the denominator and first of all write it in the factored form and observe what kind of factors you have in the denominator. And these are the possible factors, at least for all the examples that we're going to be seeing and doing in the calculus course. So the possible factors are the following. We can have a linear factor or factors. It can be more than one. Linear factor is the binomial of degree 1, and that's the structure of a linear factor. A and B are some real numbers. A can be 1, right? So you might not have a coefficient in front of x, and B can be either positive or negative, so you can have x plus a number, x minus a number. So for example, over here, so the factors of the denominator here are 2 linear factors. X plus 1 is a linear factor, and then x minus 5 is a linear factor. So you need to make sure that you recognize them. And another option is that factors of the denominator could be irreducible quadratic factors. Now, what kind of form they can have? Well, irreducible quadratic factor can come in the form of a binomial, just 2 terms. Well, that second power makes it quadratic, right? A and B are some numbers, but it's going to be irreducible. What does it mean irreducible? It means that you cannot split it up or you cannot factor it any further, right? You cannot split it up as the product of two linear factors. It's going to be irreducible if you have a positive number sign here, so always. So it's going to be irreducible only if it's with a plus sign. Now, if it's with a minus sign, then we can factor it, and you might remember the difference of squares formula, where we can split it up into two linear factors. So it has to be a plus to be called irreducible. Or a reducible quadratic factor can come in the form of a trinomial. But now, in which case we know that it's irreducible? In which case we know that it cannot be split up as the product of two linear factors? Well, it's going to be irreducible, and it says here, if its discriminant is less than 0. Now, what is the discriminant? Discriminant is this expression, b squared minus 4ac. So, and a, b, and c, you know what they are, right? Those constants from the quadratic expression. So if that is less than 0, and hopefully you recognize this expression. You might not remember the name of a discriminant, but hopefully you recognize it because it comes from the quadratic formula, right? Remember quadratic formula? So that expression that sits inside the square root, that's what we call discriminant. So this one over here, that's quadratic formula. Now, it says, okay, once again, it says that quadratic expression is going to be reducible if that expression inside the square root is less than 0. What happens when that expression ends up being less than 0, like -4 or -7 or -10? Well, remember, in that case, we get complex roots, right? So square root of -4 is 2i, right? So we get complex roots. And that's why we wouldn't be able to factor this quadratic trinomial or rewrite it as the product of two linear binomials, because we get complex roots. Now, if it's not less than 0, if it's greater than 0, or it equals to 0, then we would be able to rewrite this trinomial as the product of two linear binomials. And if that's the case, we have to go ahead and do that. So we only stop if quadratic factors in the denominator are reducible, then we keep them as they are. Now, why do we need to think about those different types? Well, because depending on what kind of factors we have in the denominator, our decomposition steps will be different. I'm going to show you a table where different cases are summarized. Let's look at it. So you can find a lot of different versions of this kind of table on the internet and in the textbooks. It's just one of them. It might not be the best one out there, but it does a pretty good job showing different cases. But this is what you want to keep in mind. So there are kind of like two things to consider. So first, what we just talked about, there are two different types of the factors in the denominator. Type 1 is linear and type 1 is quadratic, irreducible quadratic. And if I go over this table, I can see that like those first cases, they all have linear factors in the denominator, right? X minus a, x minus b, x minus a. Now, that second power, what it means, we're going to consider this still linear factor, but it's just repeated. How do I know it's repeated? Well, because it's the second power, so it means that I have two of those, right? It's x minus a times x minus a. But all those are linear factors. In this table, the only quadratic factor is shown down here. See how it's quadratic? Now, this is what you need to know about partial fractions or partial fraction decomposition. So when you note what kind of factors you have in the denominator, each factor will have its own fraction on the right hand side. So this expression would be decomposed into this sum. And that's where you start, that's where you end, right? That's kind of the idea of this table form of the partial fraction. So each factor of the denominator will have its own fraction and it's going to have its own numerator. So, and this is how you want to think about it. If denominator is the linear and this is how you want to think about it. If you have a linear factor, then its fraction will always have numerator that's a constant. So a represents constant and b represents constant. So if denominator is a linear factor, then numerator will always be constant. We have to use different letters here so that we indicate there are different numerators, right? So all linear factors in the denominator, they all have just one constant in the numerator. However, if we look down here and we observe what happened to the fraction or rational expression that had quadratic reducible denominator, notice how its numerator, it's a linear factor, so it's not a constant anymore. It's a linear factor, so it's bx plus c. So when we decompose or when we set up partial fractions in the decomposition process, that's what we have to keep in mind. Above linear factor, it's always going to be constant, just a or just b or just c or just d, and so on and so forth. But above the irreducible quadratic factor, you will always have to put linear expression like that, bx plus c. Now, if you have to create another fraction with quadratic expression in the denominator, then you could just have to use different letters. So it's going to be dx plus, what is it, e, right? bx plus c. Next one will be dx plus e. So I'm just saying that you have to keep using different letters, but the structure, the form of that expression will be linear. So basically, numerator is always 1 degree less than the denominator. Denominator has degree 1, numerator has degree 0. Denominator has degree 2, numerator has degree 1, right? That's one thing you have to keep in mind. And the second thing that I have to keep in mind is you have to observe whether you have a single factor like that or if it repeats. It's going to repeat if you see a power or if you just see how it's written, x minus a times x minus a, right? So it like really repeats, or the power indicates that it repeats. Now, what happens when factor repeats? Whether it's quadratic factor or linear, same idea for both. Well, then when you create partial fractions, then you have to do it this way. Okay, so I'm going to use this example right now. I have x minus a to the second power. It's a repeated linear factor. That means that I'm going to create partial fraction for that factor raised to the power 1. It's right here. And then next raised to power 2. So I have to create all powers starting from 1 up to the original power. So here's another good example down here. Notice how I have x minus a to the third power, so it's a repeated linear factor. That's why I'm going to have on the right hand side x minus a to the first power, x minus a to the second power, and x minus a to the third power. So I always go from power 1 up to the highest power. And all the numerators are constants because, again, we're treating this as linear factors. So above linear factor, numerator is always a constant. That would be the same idea if we had repeated quadratic factor. For example, if it was to the power of 4, then I would have one fraction with just that expression in the numerator, in the denominator, plus next one would have that to the power 2, then that to the power 3, and then that to power 4. So I would have like 4 fractions here, right? So we have to go from power 1 up to the one that's present. It's not, example like that is not shown here, but again, it's the same idea for linear factors and quadratic factors when they're repeated. In other words, raised to powers down here. Now, it might be like a little bit too much, especially if you didn't have experience with partial fractions before. It might be too much to intake for now, but by doing examples, that's how you will, really understand the concept. So we're going to finish this by doing one example where, again, we're not integrating yet, but just finding the partial fraction decomposition. Let me show you how this process works. Okay, so you start with the rational expression. I'm going over my checklist. Polynomial and polynomial, right? These are polynomials. Do they have common factors? I won't know, well, I think I kind of know, it's a pretty easy example, but technically I would not know until I factor numerator and denominator. There is nothing to factor in the numerator. However, I can factor the denominator. X squared plus x minus 1, it's a quadratic trinomial, but it's factorable. I can just apply basic factoring technique here. So there's nothing fancy in this example. Remember, it's x in each, and then I have to come up with numbers such that their product is -2 and their sum is +1. So I think it should be +2 and then -1, right? So 2 times -1 is -2, and the sum is +1. Okay, that works. Okay, so once I factor, then I check. Do they have common factors, numerator and denominator? Well, obviously they don't, right? So, but I check that. Now, degree of the numerator is less than degree of the denominator. That's true. Degree 1, degree 2. So I'm good. And then now I need to observe what kind of factors I have in the denominator. Well, here they're both linear and they're not repeating. X plus 2 is just once, written once, and x minus 1 is written once. They're not repeated. So that means that to decompose this into partial fractions, I will set up two fractions, and each will get one of those factors from the denominator. So my first one will have x plus 2 in the denominator, and my second one will have x minus 1. So each factor is going to have its own fraction, and even more if I have repeated factors, or the powers, right? So here it's just one for each. Now, once I set up those fractions, I need now to put something in the numerator. And that's where I need to remember that if my denominator is the linear factor, the numerator will be always a constant. So A represents some kind of constant. And again, here it's a linear factor, so numerator will be just a constant. I cannot reuse letters. I have to always keep using different letters, so it's going to be B. That's how I start. So that's basically what this table gives us, right? So kind of like the first step. This is how you start. Now, what do you do next? Next, you would want, once you kind of like split it up, but in general, right? So our goal is right now to find what A and B are, right? So we need to find those values. Now, so first you split the fractions like that, according to, those rules. And then you combine them again. So step 1, split, see the table, and then step 2, combine. How do we combine? Well, we just practiced at the very beginning of this video, right? To combine two fractions, that's that story. To combine two rational expressions, I'm going to use same rules as for combining fractions. So they have to have same denominator, which means that I have to multiply what's going to be the LCD, right? The LCD will be the product of those two. So the first fraction is missing x minus 1, but I have to multiply on the bottom and on the top. And the second one is missing x plus 2. And I'm multiplying on the bottom and on the top. Well, then I'll continue. I'll say that the denominator is now, well, x plus 2 times x minus 1, but the numerator is a times x minus 1 plus b times x plus 2, right? Well, I'll continue to simplify. What it means to simplify, same thing that we had with numbers. We have to distribute a, we have to distribute b. So it's ax minus a, right? I'm distributing. And then distributing b plus bx plus 2b. X minus 1. Now, what's next? Next is the important step. This is how we think about it. We started with this expression, and we have equal signs here, so it's like a chain of steps, but every new expression is equal to the previous one. So they're all equal, right? Now what I want to do, I want to look at where I started and where I ended. In which case those two expressions, so that one and that one, will be equal. Well, denominator is already equal, right? But in order for that original expression being equal to what we're looking at, numerators have to be equal this as well, right? So I'm going to set the numerators equal. So I'm going to just write down the numerators. I know that those expressions are equal only if numerators are equal. So I'm going to set the numerators equal to each other. And like what I am trying to find here, remember, we need to find a and b. So we need to find values of a and b. Well, that will help us to find values of a and b. This is how I'm going to think. If that's the numerator of the original expression, well, that has to be that same expression. So basically, I need to find values of a and b so that the original numerator equals to the resulting numerator, right? And my goal will be to literally compare them term by term. So I would want to compare coefficient of x in the original expression with the coefficient of x in this expression. And I would want to compare the constant from the original expression, well, which I don't see, but guess what? It's 0. I'm going to rewrite it like that. 3x plus 0. I need to see a constant. It's 0. So then the constant from the original expression should be equal to the constant in this new expression, in the resulting expression. Now things are all mixed up here, so now I'll need kind of to sort them out. I want to put all x's together. In fact, I'm going to put x's together and I will factor out x so I can see the coefficient. So if I take those two terms and factor out x, I'm going to get a plus b times x, right? A plus b times x. And then negative a plus 2b, negative a plus 2b, those two don't have x's, so they're constants, right? And now I will like literally compare them and set them equal. So in order for the left hand side to be equal to the right hand side, coefficient of x should be equal, on the left, should be equal to the coefficient of x on the right. Set equal. And constant from the left hand side should be equal to the constant from the right hand side. By the way, the constant is this whole expression, right? A is the constant, b is the constant, so their combination, the linear combination, is also the constant. So set equal. And by doing that, we will be able to find a and b. So we're going to end up with a little system of equations. So a plus b must be equal 3, right? And then negative a plus 2b must be equal 0. And that's how we get a little system of equations that we need to solve. Try to refresh methods that we use in algebra to solve systems of equations. So two popular ones are elimination method. That's when we add equations term by term in order to cancel one of the variables. That's actually a perfect method for this system, right? If I add equations term by term, a's will be canceled, I will be able to find b's. Or we also have substitution method. That's when you get one of the variables by itself and you plug in the resulting expression into the other equation. So hopefully that rings the bell. So here, as I said, the good method is elimination method. It's also called addition method. If we add equations term by term, we're going to get 3b equals 3. So from here, b equals 1. b equals 1, right? And now if b equals 1, then what is a? So I can just plug in 1 into, let's say, first equation in one of those. It doesn't matter which one. First one looks good. So a plus 1 equals 3. And that means that a equals minus 1 minus 1, a equals 2. So we found that a is 2 and then b is 1. And what are those numbers? Where do we put them? Well, we put them over here. So those numbers tell us how we need to decompose or split this rational expression into sum of two simpler rational expressions. Let me put this together. So 3x, that's the original one, 3x over x plus 2 times x minus 1 equals, and then, okay, so a is 2, b is 1. Here I have to put 2, and here I have to put 1. 2 over x plus 2, 2 over x plus 2, plus 1 over x minus 1. And that's how we would need to, or that's how we decompose or obtain partial fractions for that expression. How do you check? How do you check your answer? And it's always a good, if you're integrating, if you have to integrate after that, then it's really good, important step to check if you decompose correctly, because if you made some mistake, and it's easy to make little arithmetic mistake here, if you made mistake, then your integration will go wrong, right? But how do you check? Well, you check by combining them together. Like if you add them together, will you go back to the original expression? We can even do it in our head. So remember, each has to be multiplied by the missing factor. So if I multiply that by x minus 1, what I would get, I'm going to make like some notes here. So if I take 2 and multiply it by x minus 1, I'll get 2x minus 1, no, 2x minus 1, no, 2x minus 2, sorry, 2x minus 2, plus, and now second fraction would have to be multiplied by x plus 2, so it's going to be plus x plus 2, 1 times x plus 2, and if I combine like terms, 2x plus x, it's 3x, and then negative 2 plus 2, it's 0. So see how we go back to the original expression? So that works. Make sure you check. Don't integrate before you check. And if we had to integrate it, then integrating those two expressions would be easy. It would be just basic substitution rule. But anyway, we'll do those examples in the next video. So that's the process of obtaining partial fractions, or it's also called partial fraction decomposition.